Okay, so outside of those announcements, the rest of the lecture is going to be dedicated to lecture content. Of course, last time we were here, we were working on an example where we were computing different tractions in the plane. Oh, hold on just a moment here. We were using this example here where I had a very simplistic uniform stress in the x direction, so sigma xx was equal to 1. All other stresses in this coordinate system were 0, and I was asking you to calculate n and s, that is the normal component of the traction vector and the shear component of the traction vector. And we went through and did this very simplistic example. This is the notes that we had from last time. And we computed the normal component. We computed the shear component. We did it both for the very simplistic case where the new coordinate system was the original coordinate system. Of course, we found the same result as we had previously. Herein, we had the example where we're using now this new coordinate system oriented 45 degrees to the other coordinate system. And we were able to calculate with that system also the normal and shear components. I think we got through the entirety of the example, although after lecture and now having had a couple of days pass, I guess I'm not 100% confident that we completed it all. So if we didn't complete it all, please let me know, and we can pick up and do anything that we may have left off. Now, based on the feedback I got from you guys during class last time, I've updated the representations of multiplication so as to not confuse the dot product with multiplication. And also I added some vector symbols over the IJK unit vectors just to make sure that those were clear. And so I think that, or at least I hope that that won't be confusing, where I could understand where it might have been confusing previously. Okay, so did we get this far? Can I get a thumbs up from you guys? Are we, did we complete this exercise or did we not?
Professor, this is Tyler. This is exactly where we would have started if we had more time last time.
I'm not sure I heard that very well. Tyler, could you repeat it?
This is where we would have continued if we had more time last lecture.
Okay, so starting at this slide, or was it one slide or two back?
No, this is where we would have started. We finished last time with the checking, like that we actually got 1 back when we multiplied the area again.
Okay, so what I'm hearing from you is that, and I added this sentence here to the slides that were previously there. So now this is where we ended. This result of having the total force being equal to 1 is consistent with not only our expectation from the setup, but also our intuition for the problem. So that's good. So, okay, so picking up then where we left off, if we're going to compute the normal component of the traction vector, and of course we also then may be interested in computing the component of stress, the normal stress associated with the normal direction, which I'm going to call sigma nn. That calculation is going to be relatively straightforward based on what we have already computed. So we had already computed the traction vector. The traction vector, of course, in this context is Tn. And then so that was the square root of 1 over the square root of 2, 0, 0. And now if we dot that with the normal vector, we're going to end up with this very simplistic calculation. So 1 over root 2 times 1 over root 2 plus 0 times whatever plus 0 times whatever is going to end up being 1/2. So 1/2 Pascal is the normal component of stress, sigma nn, oriented on this new normal face. Now, of course, the normal component of the traction vector is that magnitude, keeping in mind that sigma nn is a magnitude. So the normal component of the traction vector is sigma nn times the normal direction. So 0.5 times n, and it gives us now a vector, because all traction vectors are vectors, so the normal component of the traction vector is also a vector. So in this case, n is going to be equal to 1 over 2 root 2 times 1, 1, 0, the vector 1, 1, 0. So 1 over 2 root 2 is a magnitude, and that normalizes essentially and then multiplies by 1/2 to get that the magnitude of the vector to be correct. Now, of course, we also needed, we were requested to compute also the shear component of the traction vector. And we could similarly, of course, calculate the shear stress, sigma ns, on this normal face. And this calculation is relatively easy also, keeping in mind that the traction vector is the sum of the components. If we know one of the components and the traction vector, we can compute the other component. So here in this case, we can easily compute S, the shear component, as just being T minus N. So the original traction vector minus the normal component. So I'm getting a question from Tyler. Thanks for the question, Tyler. I see it. It says, how do you go from Tn being a column in the last lecture to a row in this lecture? So let me just jump back there to answer his question. So when you're doing a dot product, what you need to think about a dot product is you can expand a dot product into the idea of the traction vector being 1/2, or I should say 1 over root 2 times the I direction plus 0 times the j direction plus 0 times the k direction. And then you can look at the normal component of the vector as being another vector. So what I'm suggesting is you could have written these vectors out in their sort of summation sense and then the dot product. And that's functionally equal to, in this case, what amounts to T transpose times N. So if we're representing vectors, 3×1 vectors as 3×1, in order to get the dot product, we have to do the transposition to make that matrix mathematics work out. So I hope that clarifies what I had done there. It's just a simple, very simple way of doing that problem. So anyway, here we go again, traction minus the normal. So there's the T, which is 1 over root 2I plus 0j plus 0k, minus the N vector, which I've also written 1 over 2 root 2I plus 1 over 2 root 2j plus 0k. And of course, that makes S quite simple also. 1 over 2 root 2I minus 1 over 2 root 2j plus 0k. Now, if you think about that and you looked back at the components that we drew on the image, you would have seen that you had a component in the positive x direction for the shear tensor and a component in the negative y direction for the shear tensor. And so that is consistent again with expectation, as we see here in this computed result. Okay, so we're going to do a slightly more complicated example. So previously our goal was to do an intuitive example that would be very easily understood and just work quite well with your intuition. Now I'm going to present you with one that's perhaps a little bit more realistic to what you might need in the real world. That is We have a stress tensor that has multiple components within it that are non-zero. And of course, we're looking at an arbitrary plane rather than a plane associated with a rotation about one of the principal axes. So, but you're going to find that this is just as easy as the last one. It's not going to be any more difficult. So we'll go through it fairly quickly. The stress tensor in this case, I'm going to give as 50, 20 minus 10, 20 minus 30, 0, minus 10, 0, 40. Of course, along the diagonal are the normal components. The off-diagonal components are shear components. And you remember, of course, the subscripts, x, 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 y, x, z, y, x, y, 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 z, and so on. The plane that I would like you to compute the normal and shear components for is shown here in this image. What I'm doing is I'm taking a plane that has, in the x direction, a magnitude of 3, offset, a y direction magnitude 4, and z direction magnitude 5 from the origin. So this plane is, pointing off in the positive x, y, and z directions. Each of the angles is a little bit different relative to the principal axes, or I should say the Cartesian axes. All right, so now you've seen how to do it. How do we do it? You, of course, remember from last time that the traction vector is simply calculated using this Couchy stress formula. That is the stress tensor dotted with the normal vector. So the only thing difficult in this problem is the essentially finding the normal vector. That's really the challenge here in this problem. So how do you go about doing that? Does anybody have a suggestion? Feel free to type in the chat box. I'm going to give you just a minute to do so. So Ethan gives us a good response. Ethan says, take the cross product of A and B. You kind of, I think, saw the hint. Tyler says the same. Good job, guys. Just drawing those two vectors on there maybe gave you a hint. So if we take A and B, Riga, did you have a question? Your mic is on, but I'm not hearing you. Okay, so A and B, of course, were identified. If we look back at that image that I showed on the prior slide, the vector A would be equal to 0 in the I direction, minus 4 in the J direction, plus 5 in the K direction. And the vector B would be 3I minus 4J plus 0K. And of course, to compute the normal to that, you may recall is the cross product, but it's not just the cross product. We actually then would like to normalize that unit, I should say that normal vector to be of unit length, because we're only trying to find the plane. So it ends up being A cross B over the magnitude of A cross B. And so this is a relatively straightforward and simple calculation. A cross B is equal to minus 4 times 3 times J cross I plus minus 4 times 5 times K cross J plus 5 times 3 times K cross I. And you guys can probably do that in your sleep. You're probably using your right-hand rule to do so and trying to remember ultimately whether it's a plus sign or a negative sign when you do the K cross I or I cross K. I'm sure you can do it, no problem. And in the end, what we get here is a vector A cross B is equal to 20I plus 12K plus 15j. Of course, the magnitude of that is just the sum of the squares, square rooted, which works out to be the square root of 769, or about 27.73. And hence, we can take the overall magnitude is going to be that. There it is. Now, if you're doing this on your homework, you can either leave it in this form or you could write out the decimal version of it, and I would accept either one as long as they're both correct. Okay, so from that, of course, then we're looking back at that Couchy formula. So what you're seeing here is the Couchy formula. The traction vector is equal to the stress tensor dotted with the normal vector. Now here I've, the stress tensor is written in the square brackets. The normal vector I left in its original form, where it's now written as a vector 2015-12 times 1 over the square root of 769. So the 1 over square root on the right-hand side just normalizes the length of that normal vector. And so we can compute very directly the traction components, Tx, Ty, and Tz is 42.55, minus 1.8, and 10.1, all in megapascal units. And again, you're, in your homework, you're allowed to write this any way that's consistent and clear. You could write it as a vector. You can write it out in this summative form, directly showing the components. It needs to be clear, of course, that it is a vector, and you do need to include units on it when it's appropriate. But I'll accept really any form as long as it's appropriate. Now, like we did with our simplistic example, we are going to do the same thing with this example, because of course I asked you to compute not the traction vector itself, but rather the components of the traction vector. So the magnitude of the component of the traction vector, that is sigma and n, and of course the n direction, both of those need to be known. We know n already. What we can do to calculate sigma n is take that traction vector Tn and dot it with n. So this is the component of the traction vector associated with the normal direction. Again, I did the transposition, put it as a 1/3 matrix, that's Tn, then multiplied it by n, which I left in this form that has the 2015-12 and then the unitizing constant on the right-hand side. And the end result is a computation that says we have 34.08 megapascals as our magnitude sigma nn. So Nicole's asking a question. Nicole asks, is Tn just the traction vector, or does the n mean it has something to do with the normal? So the scheme that I'm using here, the notational scheme that I'm using here, is that this is the traction vector associated with the normal n. So T sub n is the traction vector associated with n. That distinguishes it from other traction vectors that may be present on different normal planes, which of course can and do exist, as we saw last time. And in fact, we're going to spend the next half of this lecture, once we finish these examples, sort of opening our mind to finding traction vectors on arbitrary planes in a way that is extremizing. We're going to try and minimize or maximize stress. And that becomes really an important calculation, extremely important calculation for us. But we'll get there in a few minutes. So sigma nn now is known. That is the magnitude of that component of stress. And so from that, of course, we can calculate the normal component of the traction vector, it just multiplies that times the direction. So n is equal to 34.08 n. So Ron's asking, is it 42.55 minus 1.8 plus 10.10? Yes, the answer is that's plus 10.10. The plus is, this is now a matrix. It's a 1 by 3 row. I dropped the pluses in front of both the 42 and the 10. But yeah, that is supposed to be 10. Okay, now the shear component, again, how do we do that? Well, it's not complicated. It's just essentially the same thing that we did with our more intuitive example. So all we need to do is subtract the traction vector, or I should say the normal vector from the traction vector. So Tn minus n is going to be equal to S. We can express Tn as, in this form, 42.55i minus 1.80j plus 10.10k minus the normal vector, which is now written in somewhat long form here. And from that, we can compute S itself, 17.97i minus 20.23j minus 4.65k. And we may also be interested in knowing its magnitude so that we can compare the magnitude to the magnitude of the normal component. And here we see that the magnitude is 27.46 megapascals. So of course, now we know the magnitude and the direction of both the shear and normal components of the traction vector. These are good outcomes, going to be useful to us going forward. Okay, so we've done it. You did it on an exam. You've got your answer, at least you think you do. What are you going to do next? So as
Sanity
an engineer,
check.
Yeah, as an engineer, you want to do a sanity check, right? You want to see if your answer makes sense. It's often difficult to know if it's correct, but it's often easy to know it's incorrect. And so you want to check at least to know if it's incorrect. So does anybody have any ideas how you might do that for this problem?
You could dot product your normal and your shear vector.
Good idea. All right, so we could do that. In fact, I think that's not the first thing I did. What would you get?
You should get 0.
Correct, yeah. So, so that's not the first one here, at least in the order of my slides. I would suggest instead to check for orthogonality. So the dot product being equal to 0 essentially does confirm that we have orthogonality. So there you go, that's that. The other thing, of course, that you could do is what? Actually, I thought I did the other one first. Apparently, I did the dot product first. Well, I won't leave you hanging. The other thing you could have done is taken the cross product of the two vectors, and then you should have gotten a third vector. That would make sense also. Another thing that you can do is you can verify the magnitude being correct. And we can go ahead and do that. So all of those things, I just want to encourage you guys as you're going through this course, and of course then subsequently in your professional lives, when you are providing people answers to important questions, to think about how you can confirm that your answer is at least not blatantly wrong. And then of course, it's a really good idea often to address the same problem from a couple of different perspectives to make sure that the answer that you're giving is right or at least feasible. Okay, so believe it or not, that was the end of lecture 4. So we're about 30 minutes behind what I had expected us to be at this point, but that's okay. We're going to just keep on plugging away. I'm going to move on now to lecture 5.
I have a quick question. How can we calculate or make sure it's correct with the cross product? How does that work?
Well, so you can, you want to make sure that if you have these unit vectors in multiple directions, that the cross product of the unit vectors, cross product of any two vectors should give you the third. That's really the suggestion that I meant to be making there. I guess really, perhaps to your point, in this context, that's less obvious and less critical. But since you know the two directions of n and s, what you could do with the cross product here is you could compute that third component and make sure it was also 0 using a cross product. Okay, so now moving on to lecture 5. This is part 2 of stress and internal equilibrium. I actually don't think we're going to get through the entirety of this lecture, so we'll probably have one more lecture that includes stress and internal equilibrium at least. But we'll go ahead and get started with this one as we are now. So what we've now done is we've learned how to compute traction vectors, traction components. Now, it's worth noting, these are just some comments really about what a traction is. Note that you've heard that word many times, I'm sure. So I've been watching the Tour de France. I enjoy watching that. And one of the things that as a cyclist, they're constantly concerned about, if you've ever watched that race, is traction. You know, when it's wet and raining, they tend to lose their wheels and go down in big crashes. There's another great video if you're a cyclist. There's a race called the Mountain of Heck, although they use a different word. And there's hundreds of bike racers going down a mountain of ice. And the 2019 version of that, one of the cyclists lost his traction and ended up starting a chain of incidents that led to at least 100 people crashing at the bottom of this major hill. So anyway, the point there is that you've heard this word before. You probably never really thought much about it, but that word, traction, is derived from this concept of traction, the traction vector. So this is usually referencing some sort of external surface boundary condition where a stress is applied. Okay, so for a bike, you're going to have a normal component of the traction that holds the bike up out of the ground, keeping it from penetrating the ground. And then you're going to have a shear component that keeps the wheel moving straight as opposed to sliding out underneath. I will mention that this is an extremely important aspect of the concepts of traction, but it's not the only application. And we're going to get to the next really important application here in the next few slides. Anyway, so this idea of attraction, what is it? What physically does it represent? Well, it ultimately represents the intensity of stress at a given point over an area of given orientation. Okay, now again, usually referencing external surfaces, but not exclusively. I'll mention that if I give you a homework problem or an exam problem as boundary conditions, I'm typically going to give you displacement boundary conditions or tractions or maybe point forces. And those are what are going to be specified as external boundary conditions. As a sort of practical note, it would be rare that I would give you both tractions and displacements. And that's because if I'm doing so, I may actually be over constraining the problem, or alternatively, I mean, certainly in all cases, when you have a solution, you have the ability to compute both displacements and tractions on those surfaces, but it would be rare that both would be given as part of the problem statement. Now, I've hinted a couple of times at this idea that external surfaces are not the only thing that tractions are useful for, and that we'll find the ability to calculate shear and normal components of tractions to be extremely important. Well, here's why. We have this concept called principal stress. Suppose we're interested in finding the plane, i.e. the normal to a given plane, that extremizes the normal stress component. So it makes sigma nn either as large as it could be or as small as it could be. Maximizes or minimizes. Now, before we get into how we do that, it's worth asking why we would do that. Why do we care? Why do we search the different planes that are possible? Of course, there's an infinite number of planes. Why do we search amongst the infinite number of planes for the plane that maximizes or minimizes the normal component of stress?
Finding the plane at which it's most likely to experience the largest force, which in turn would experience the most likely chance of breaking or fracturing.
Great, thanks, Scott. Very good answer. The only thing that I would minorly tweak about that answer is that you use force, and I would say instead stress. But yeah, absolutely, you're 100% right on the nose. So an example of that would be that, you know, if you have cracks that form, they tend to propagate tangentially to the maximum normal stress component. So when you're pulling on something, it'll either fracture and have a fast fracture that'll open and catastrophically fail, or in the case that it fractures slowly, it'll at least open that crack perpendicular to the maximum normal stress component, typically, unless there's some sort of material grain or something that it would then instead follow. So very good answer. Thank you for that one. So of course, then the next question is, how do we do it? How do we find it? And the answer to that question is, you need to think back to vector. I'm going to say step back from tensors to vectors and think about how you can find a component of vector that maximizes the length of the vector in that coordinate system. I don't know if you're able to see me. I do have, of course, my video going. I'm holding up the pen that I'm using for the class. I'm going to use that as my vector. I have my right-hand rule coordinate system. I'm only going to use 2 fingers to represent because this is essentially a 2-dimensional problem for now, but this concept generalizes to 3 dimensions. So in the XY space, I've got this vector that's aligned with the direction. It has components in both the X and the Y direction. My goal would then be to find an orientation by rotating my coordinate system that extremizes the length of that vector in the coordinate system. And I think you guys would agree, again, thinking of it as a sum of vector components, that I have really 2 choices in this context. I either have this orientation, where what I had originally drawn as the y-axis is now aligned with that vector. Or alternatively, I have this orientation where what I had originally aligned as the x-axis is oriented with those coordinate systems. Now, either of those 2 extremize the component of the vector in that orientation. And what's notable is the other component in this orientation is 0. So to find the maximum normal component, in fact, all we really need to do is find the component where the shear stress is 0. Now, conceptually, that may not be easier for you to take a guess at how to do it, but in practice, it's actually much easier mathematically. So we're going to go ahead and do it. So here's our traction vector. I'm writing it as a, we're trying to find the orientation. So I'm finding a new coordinate system where the shear component S is equal to 0. Of course, we remember that the traction vector itself, Tn, is equal to the sum of n plus s. And because s now is 0, we know that the traction vector itself is simply going to be equal to n. Now I see a question coming in. Jeremy asks, to be clear, the length of the vector is not changing, just the way we describe it to have a maximum axis value. So yes, that's correct. Of course, a vector, what I was doing with my fingers here is a vector transformation, and conceptually we're going to generalize that to tensors, higher ranked vectors. So it's in the context of stress, it's a second rank tensor. But either way, the vector stays the same, just the components of that vector, the coefficients associated with the direction vectors change as you change the orientation. So we're finding the orientation where those component coefficients are the largest with the same vector. So thanks for the question. It's a good one. Okay, so getting back to where we were. Here we have the traction vector is then equal to n, the normal vector, which of course we also know is going to be equal to the magnitude of n. So the two vertical bars there represent magnitude of n, now multiplied by the normal direction. So Tn is now equal to a magnitude times a normal direction. And last but not least on this slide, Tn is therefore going to be equal to something we're going to call sigma p times n. Now sigma p is just the magnitude of that normal component of stress. And of course, it is now oriented in the n direction. So this magnitude, sigma p, we're going to call it the principal stress. Now the orientation of that principal stress, which we'll now call n, we're going to say is a principal orientation, or also called principal axis. So it's important to recognize we have not only a principal stress magnitude, but also a direction. Both are equally important to be able to identify. Okay, so that's conceptually how we're going to do it. Now, I want to actually accomplish that goal. So here's how we accomplish that goal. Of course, the traction vector itself, just using that Couchy equation again, you'll see it comes up quite frequently. It is the stress tensor dotted with the normal vector. Now, the only thing that's funky here is we don't know the normal vector yet, okay? But nevertheless, we know that the stress tensor dotted with this unknown vector is going to be equal to the traction component, Tn, which we also know is going to be equal to the magnitude of the traction times its direction. So right-hand side, sigma p times n. Okay, now we can do a little bit of mathematical manipulation. We move the sigma pn to the left-hand side. So sigma dot n minus sigma p times n is equal to 0. 0 on the right-hand side of vector. And looking one step further, we can see that that sigma p needs to be multiplied by an identity matrix in order to collect the terms. So sigma, the 3 by 3 matrix, the tensor, minus sigma p times I, the identity matrix, 3 by 3, dot n is equal to 0. Okay, now, so I've set the problem up. I wonder if anybody recognizes this problem. Is this a problem that you've ever seen before? Ethan says, it looks like we're finding an eigenvalue. Great, thanks for not leaving me hanging for too long there. You're absolutely right. So what we're finding is an eigenvalue. Now, this is actually by more than coincidence. This is the very definition of the eigenvalue problem. With sigma p, there's a missing symbol there, with sigma p representing the eigenvalues of sigma. This is how we set them up when you were studying how to solve eigenvalue problems. Sigma xx now is the component minus sigma p, and then of course the other terms. The normal terms are all subtracting sigma p. The shear terms are left alone. We now have this unknown normal vector L, M, and N, which is going to multiply that, and then the end result is 0, 0, 0 on the right-hand side. So if you went through and you did this manipulation, you'll recognize that non-trivial solutions, and this goes back to your days as a freshman or sophomore, non-trivial solutions to this equation can be determined by setting the determinant of that matrix, sigma minus sigma pi, equal to 0. Now, when I say non-trivial solutions, I want to make sure that that's clear. Can anybody propose a trivial solution? So, of course, the trivial solution here is going to be 0, 0, 0. That is L, M, and N would be 0. So that would be no unit vector. Of course, that's trivial. It's meaningless. It doesn't help us in any way. So we're trying to find the non-trivial solutions. So again, to find those, you need to have the determinant of this matrix and set it equal to 0. Now, of course, computing the determinant is something you may have forgotten how to do. It's not terribly difficult. In your homework problems, you're going to go through and do it, so you'll quickly remember if you had forgotten. But basically, you take the top left corner and multiply it by the minor determinant of the bottom right, 2 rows and columns, and then you subtract from that the middle top times its minor determinant, and then you add to that the upper right times the minor determinant of the lower left, a 2 by 2 matrix. Anyway, long story short, in the end, what you get is a big polynomial equation. It's a third order polynomial equation in sigma p. And then you put it in this standard form where the sigma p itself has a leading coefficient of 1, even if it numerically previously did not. You want to then divide by whatever was the leading coefficient, so that sigma p is of leading coefficient 1. Minus, now another coefficient we'll call I1 times sigma p squared, plus another coefficient I2 sigma p, minus a last coefficient I3, and that is going to be set equal to 0. So that's the determinant, going to be equal to 0. And ultimately, the roots of this characteristic equation, third order characteristic equation, are called principal stresses. And by convention, we order them according to their magnitude. I'm sorry, not magnitude, actually their absolute value. So that sigma p is the largest in absolute value and sigma 3 is the smallest in absolute value. So 1 is greater than minus 10. So if you had 1, 0, minus 10, sigma 1 would be 1, 0 would be sigma 2, minus 10 would be sigma 3. Now I should mention what these I values are. The I values, we put the I in front of them because they're called invariants of the stress tensor. Okay, the characteristic equation doesn't change as the stress tensor is transformed. Now again, I want to make sure everybody's clear on what I'm saying. If you're looking at my face in the video, again, what is a transformation? That's as we reorient our coordinate system. The vector stays the same. Okay, it doesn't matter what the coordinate system is. The magnitude and direction of that vector needs to be maintained. Earlier in the semester, I said for higher ranked tensors, we need to do not only magnitude and direction, but additional things. So those additional things here for this second ranked tensor are the so-called invariants. These invariants don't change as we observe the stress tensor from different coordinate systems. Now, these are very common things that need to be computed frequently. And so you've probably heard of a couple of them. So the trace of the tensor, that is the sum of the diagonal x, x, y, y, z, z, is something that we call in structural mechanics the hydrostatic stress. Really all it is the trace of the tensor. So if you had a strain, it would be the trace of the strain. If you had, there are other disciplines where we would not call it hydrostatic stress, but here in this context, the trace of the tensor is the invariant. We give it the name hydrostatic stress because in mechanics, that's something that's actually an important concept, hydrostatic stress. Okay, the next one actually doesn't really have a fancy name. It's not something you're going to see expressed too frequently, but ultimately, we're going to call it I2, and it relates the strength of the deviatoric stress relates to the strength of the deviatoric stress, meaning if you take the advanced structural mechanics class, AE5100, we'll get into this into a lot more detail, but this is a driver of plasticity in a material, okay, especially in a ductile material. And then last but not least is I3. This one's extremely common. You've heard of it before, the determinant of the tensor. And that's, of course, the determinant of the original stress tensor, not the modified stress tensor. Okay, so now we've done it. We've calculated principal stresses. It's worth noting that because stress always is a 3x3 matrix, or it's a second rank tensor with 9 components, it will always have 3 principal stresses. So we should always compute 3. Sometimes that means that one of them will be 0 if we have a planar stress field with no out-of-plane components. But nevertheless, we should recognize that there are 3 principal stresses. Okay. Also, because each of these 3 principal stresses have different magnitudes conceivably, they could each have different principal stress directions. And in fact, in most cases, they do. It's actually rather unusual that you would have that not be the case. We'll cover those corner cases in a few minutes. But for the time being, we just recognize that because we have 3 principal stresses, we have 3 principal directions. And so now I need more normal vectors. So I'm going to use n sub I. Now the subscript I is representing whether it's principal stress 1, principal stress 2, or principal stress 3. And they're now determined from this set of equations. So sigma x minus sigma I, and the remainder of the modified stress tensor, ultimately dotted with LI, MI, NI, is going to be equal to 0, 0, 0. I just want to confirm that you guys are still with me. For whatever reason, the students whose faces I can see right now are all locked up. Nobody's moving. I assume that maybe there's a network problem. Can you confirm that you can hear and see me?
Can hear just fine. Yes.
Great. Great. Thank you. Okay, so a couple of brief notes about principal stresses and orientations. So the principal vectors, principal orientation vectors, are normalized by convention to have unit length. Unit vectors have unit length. And it turns out that they are what we have called in the past eigenvectors of the stress tensor. So we have eigenvalues, which are principal stresses. We have eigenvectors, which are principal orientations. I always think it's a little odd that we teach you this concept, 2-3 years ago, and then we let you forget it before we actually use it. It's that concept that we taught you so long ago is actually really critical for calculating material behavior and ultimately failure. These are failure metrics is what we're seeing, material failure metrics. And so I'm glad that we're finally using that skill that we taught you so long ago. So what we computed were principal stresses. Now, by definition, as you saw, those are the components, the normal components of the traction vector in orientations where the shear stress was 0. So what we found was the maximum value of the normal stress, the minimum value of the shear stress. Now let's go back to this two-dimensional vector. Here's my pen. Okay, again, I have my coordinate system. We're doing it in 2D, not 3D. Okay, this is what we said was an orientation that maximized the normal component of the vector. This was another one. Now it's notable that we also want to be able to find an orientation that maximizes the shear component. And intuitively, what are we saying? So this is the orientation where that second magnitude is the largest. And as I rotate around in this two-dimensional world to a 45-degree plane, this one has it has equivalent normal and shear components in this two-dimensional vector. And so that's the orientation that maximizes the shear component in this two-dimensional world. Now, it's not quite as clean as that in the three-dimensional world. What we find is that the maximum stress, the maximum shear stress, I should say, the maximum magnitude of the shear stress in magnitude is going to be 1/2 sigma 1 minus sigma 3. And it's going to be on these planes. The local maximum are on the octahedral planes. Turns out there's 8 of them that are functionally equivalent. They're 45 degrees offset from the principal directions. They bisect the principal planes. That's what that word means, 45 degrees offset. And the maximum of all those shears is going to be sigma 1 minus sigma 3 divided by 2. That's a magnitude now. Now this, of course, is also going to be an important mechanical concept, the maximum shear stress, because this very much relates to yield in ductile materials. So the maximum normal stress is really critical for brittle materials because that has to do with crack propagation. And it turns out the maximum normal stress also is critical to materials that yield, that i.e. ductile materials, except it's a little bit backhanded, meaning that you first need to calculate the shears. But we'll get into that, if we'll spend a little bit more time on that later. Okay, so here we go. I want to do a quick example so that you guys can confidently move forward knowing you know how to do this. So the example here, given a stress state, sigma 110110001, find the principal stresses, principal directions, and maximum shear stress. Okay, so what do we do? It's just a few slides ago. Bring it back up. Well, the solution, of course, is we find the invariants and then ultimately the principal stresses. So we set the problem up. We actually write 1 minus sigma p, 1, 0, 1, 1 minus sigma p, 0, 0, 0, 1 minus sigma p. We take the determinant of that matrix. We take the characteristic equation that results. We make sure to put it in standard form, so the leading coefficient on sigma p cubed is 1. And then we look at what the other coefficients are, and here are what they are. So I1 is going to be equal to 3. I2 will be equal to 2. And I3 will be equal to the determinant of the original matrix, which works out to be equal to 0. Now, if you choose to, you can do what I've done here on this particular slide, and that's just use the equations for I1, I2, and I3 that I presented you earlier in terms of the components of the original stress tensor, sigma x, x, y, y, z, z, x, y, y, z, x, z, and you just plug in the numbers and chug. That's what I'm doing here. But really what you conceptually need to recognize is how to do the problem, and that's ultimately to take that determinant and reconfigure the characteristic equation. So here we have I1, 2, and 3. Here's the equation now where we've written the characteristic equation in standard form. So sigma p cubed minus 3 times sigma p squared plus 2 times sigma p plus 0 is equal to 0. And we have to solve this equation. So how do you solve that equation? Well, you probably would have to go back to high school algebra perhaps to solve it, or maybe freshman year of college, depending on at what point you managed to pass through this mathematical system. I think there are a number of good ways to do it. You can plot the roots. You can plot this equation with respect to sigma p and then find where the roots cross 0, or you can find where the value of this equation crosses 0 to find the roots. That's one way to do it. The way I like to do it when it's simple is to just factor the equation. So here by inspection, we could factor the equation and determine that sigma p is equal to 2, 1, and 0. I've ordered them conventionally, 2 being the largest in absolute value. So that's sigma 1, 1, and 0. So sigma 3 is equal to 0. Now, of course, we found the principal stresses, but we have not yet found the principal directions. And we know that these principal directions are important. So we'll go ahead and find the principal directions. Here, what we have is, and basically all you're doing is you're plugging sigma 1 into the original equation. So 1 minus 2, 1, 0, 1, 1 minus 2, 0. 0, 0, 1, minus 2, which of course simplifies, as you can see on the screen, minus 1, 1, 0, 1, minus 1, 0, 0, 0, minus 1. That new matrix, really a tensor, dotted with L1, M1, N1, the unit vector, has to be equal to 0. So this is a rather trivial exercise. So just looking at equation 3, let me go back to equation 3 for a moment. Equation 3 that's this equation. And if we examine that equation alone, what we see immediately is that N1 is 0. Of course, we can then look at the second equation. Oops, sorry about that. Wrong direction. That one is going to be equal to 1 times L1 minus 1 times N1 is equal to 0. And from that, we can, by inspection, say that L1 is equal to M1. Okay, so we still don't know L and M, but we do know N. What's the last step? So pause for dramatic effect here. Usually a student volunteers, well, use the first equation, right? So you got 3 equations for 3 unknowns. Oh, David says parameterize. What does that mean, David? Be more specific.
Kind of remember it means writing it in terms of unknown constants.
Okay, and the unknown constants are what here?
I don't know that part.
Ah, good. Okay, so what we really need, so we need 3 equations and 3 unknowns, right? We have 3 unknowns. We need 3 equations. We've used 2 from the matrix representation. So you might intuitively think, well, let's use the third one, but in this case, that wouldn't be correct because we know, in fact, that these are redundant equations. That's the whole concept of the eigenvalue problem. If we had 3 equations and 3 unknowns where all 3 equations were unique, we'd be able to solve for those 3 unknowns without doing the eigenvalue problem. But the definition of the eigenvalue problem is, in fact, that one of those equations, at least one of those equations, is redundant. I'll go back for a moment here. So if you stare at equation 1 and equation 2, minus 1, 1, 0, 1, minus 1, 0, keeping in mind that if we're just solving equations, you can multiply all of the first equation by some constant, and you haven't really changed the equation in terms of solving for the 3 unknowns. And so we could multiply the first equation by minus 1 and identically turn it into the second equation. And so it's redundant. It hasn't helped us. So we actually need to come up with a third unique equation. And there's no trick to it here with these eigenvalue problems where we're calculating unit vectors. The last equation for our purposes is always going to be this one. That is that the magnitude of the unit vector is 1. So we already determined that L and M were the same. So therefore we have L1 squared plus L1 squared plus 0. The third one we already determined is equal to 1. And so from that we can determine that L1 itself is equal to 1 over root 2. And then we can write the whole unit vector, principal direction, N1 as being equal to 1 over root 2 times 1, 1, 0. Okay, so we've done it once. We have 1 principal stress. Actually, we have all 3 principal stresses, but we only have 1 unit vector. I'll move through these other ones fairly quickly. It's not, this is not really rocket science at this point. It's pretty obvious. So the second principal direction is the one associated with sigma 2, i.e. the second principal stress. So we just plug and chug 1 minus 1, 1, 0, 1, 1 minus 1, 0, 0, 0, 1 minus 1. And we get this matrix 0, 1, 0, 1, 0, 0, 0, 0, 0 times L2, M2, N2 is going to be equal to 0. We kind of do the same thing that we did last time. It's often easy. Well, I set this problem up specifically to be easy, but we can look at these equations and make some bold statements right away. So the bold statement that I'll make is that inspection of both equation 1 and equation 2 immediately gives us the magnitudes of L2 and M2. Okay, again, you can see this is this equation here. and this equation here, we know that L2 and M2 are both going to be identically equal to 0. Then the last thing is, how do we find N2? Well, of course, if we looked at N2, 0 times L2 plus 0 times M2 plus 0 times N2 would give us 0 automatically, but that hasn't told us anything about what N2 is. Again, we have a redundant equation here, or at least a useless equation because it's all 0. And therefore, we need to then use that technique of taking the magnitude of the unit vector and make sure it's equal to 1. So L and M are both 0. That means N2 squared is equal to 1. And so therefore, we have N2 being equal to 0, 0, 1. Okay, so at risk of getting boring and letting you guys fall asleep, I will continue and do the third one for completeness, but we're going to move through it very quickly. So the third principal stress was 0. Okay, nevertheless, we still need to do the calculation. So here's the calculation. And this looks, in fact, quite similar to the first calculation. It's a little bit different. We had some minus signs in the first principal direction calculation that we don't have here in this calculation. But we can use the same process. So inspection of equation 3 showed us that N3 was equal to 0. And then, of course, we can look at equation 1. So let me go back and just highlight these. Okay, so this equation was, oh, shoot, I guess I've lost my ability to edit. Go back and inspect equation 1. And we can see in this equation, we can see 1 times L3 plus 1 times M3 plus 0 is equal to 0. And from that, really, we're seeing now L3 and M3 are opposite of each other in a minus sign sense. So L3 is minus M3. And then, of course, we can place that into this same magnitude of the unit vector is equal to 1 calculation. And of course, the minus sign goes away when we square. So 2L3 squared is equal to 1. L3 is still equal to 1/2. And N3 now is equal to square root of 1/2 times 1 minus 1, 0. If you recall from the first principal calculation, it was 1, 1, 0. Here it's 1 minus 1, 0. Okay, so we've essentially completed the problem. You know, again, you've gotten to the end of your exam. You're fairly confident in your answer. Is there anything you can do to ensure, to check, to sanity check your result? Of course, yes, there is. By the way, when you get to the end of your answer, you should summarize it. Okay, you don't want to leave unit vectors hanging out all over the place. So bring them all together. A good way to represent them is actually as a set of column vectors. So the column vectors here, square root of 1/2 times 1, 1, 0, 0, 0, square root of 2, and 1 minus 1, 0. So they're all succinctly in one place. And then, as I mentioned, it's a good idea to sanity check. So what are we going to do? Again, similar to what we had done in the prior set of problems, some things stand out. So these are unit vectors. They are defining a coordinate system. So again, we can think about dot products and cross products. Dot products of two unit vectors, assuming it's not I dot I, but rather is I dot j, are going to be 0. And of course, cross products, I cross j is going to be equal to k. So we can do each of those and check essentially for orthogonality. So here we have N1 cross N2 going to be equal to N3, at least we hope, after we do the calculation. How do we do that? So here's just a way of representing that cross product as a determinant of a matrix. I don't know if you've seen that representation of cross products before, but it's fairly straightforward. And what we find is that N1, N2 given as A and B end up being equal to N3. This is the calculation for N3. And oh, by the way, that checks, that worked out. I'll go back to that slide. I know some of you are copying it down by hand. I don't want to rush you. So it's always a good idea, as I said, to check, check whether your answer is sane. It's good and easy to do for, comparing unit vectors. Perhaps a little bit more difficult to do for computing the principal stress values themselves. But you could, if you wanted to sanity check your principal stress values, now that you know the unit vectors, you've gotten to the end, you could go through and use the Couchy stress formula. You could dot the stress tensor with the unit vector. You'd get a traction vector. You could dot that with the traction vector, and you should be able to, or you should say you dot the traction vector again with the unit vector. So you're going down 2 ranks by doing 2 dot products and get to the principal stress value. That would be a way to sanity check that answer as well. I don't demonstrate that here in the lecture notes, but it's fairly straightforward. Okay, a couple of additional thoughts on principal stress. So what are they? Again, physically, what are they? They're the largest normal stresses on any plane. They're on orthogonal planes, in fact. So that's an important realization, is that these normal stresses are each oriented in 3 different directions, orthogonal to each other, and they're extremizations. They're the maximum values of the principal stress or the normal stress components. This, of course, occurs where the shear stresses vanish. And again, as I mentioned, the coordinate directions are called principal axes. We've identified that previously. What else can I say? Well, I mentioned these unique kind of corner cases where you may have principal directions that are a little bit funky. Now, what I meant by that was the following. It is certainly possible, and in fact not entirely infrequent, that you have 2 principal stress values after you've calculated the characteristic equation and you found the roots of that characteristic equation. You found that 2 roots were the same. That means 2 principal stresses are equal. And what you'll find when that is the case is that you're not going to find unique unit vectors associated with those 2 identical principal stresses. In fact, what you're going to find is that 2 principal axes are arbitrary in the plane. Okay, at some point during the semester, you're going to explore that a little bit more, probably in a homework set or in an exam. So be ready for that, be looking for it, be thinking about it. What does it mean? It means that in a particular plane, the stresses are equal biaxial. You're applying stress in 2 different directions at equal magnitudes. Then as you were to rotate in that plane, if you're going to observe how that influences the components of stress, you would find that as you rotate in that plane, the component magnitudes don't change. Now, if you can do it with 2 vectors, it's conceivable that you can do it with 3. That does happen periodically. If all principal stresses are equal, then all 3 axes are arbitrary. And then we have this state of what's called hydrostatic stress. Okay, this actually does happen in the real world. First of all, if there's no stress on the structure, then the stress everywhere is 0. You've got identical principal stresses of 0, and so therefore you have an arbitrary axis at which that's applied. That's the trivial case. The less trivial case, of course, is when you have, let's say you drop a structure, a submarine, down into the Marianas Trench. You've got these equal stresses being applied external to a sphere. If you drop the sphere down into the Marianas Trench way down there, you'd get very high stresses, but they'd be uniform, hydrostatic, equal on all sides, equal in all directions. That's the kind of unique case where that shows up. It's perhaps not common, but it exists. Okay, so it is 3:50. So we are getting close to 3:50, I should say. We've essentially used up our 80 minutes for the day. We do have a whole nother lecture essentially on stress and equilibrium. So we'll be ready to do that next Tuesday. It'll pick up at this point here. I'll pause. I'll stay on the line here for a little while, take any questions that you guys may have. Otherwise, have a great weekend, and I'll see you next Tuesday. Be looking for the next homework set. Be looking for the returned homework set 1. If you have any questions, feel free to let me know.
I have a question. For the n vectors we are finding, lowercase n, is it always going to be 3 or less, or can it go to higher orders?
Well, because we have 3 principal stresses, we're always going to have 3 principal directions. Now, the caveat to that is the caveat that I just gave, that when you have repeated principal values, that you then lose the uniqueness of the 3 principal orientations. Now, what that means is that within a plane, all the orientations within that plane are sort of equally valid principal orientations, or by that argument, equally invalid principal orientations. They're arbitrary in that plane. So, they're not, if you were, so let me say it this way. If you were given that problem on an exam and you had repeated roots, and then you defined for those repeated roots unique principal stress directions, you would be wrong. And so I would mark you down for that, because they're not unique. They're arbitrary. They could be any set in that plane. So it wouldn't be that your set was totally incorrect, but it's not the complete and correct answer. You're never going to have more than 3, if that was the other part of the question. So Tyler asks, why then you wrote out the symbolic tensor for finding principal stresses? Do you have the non-diagonal elements mirror each other in tensor notation? Tyler, why don't you get on, unmute yourself and ask that again. It's not entirely clear what you're asking.
So like when you wrote out the tensor, you had like sigma x, y in the second column for the first row, but then you also had it written sigma x, y in the second row, but the first column.
Okay, I'll go back to that. That's a great question. I'm trying to, let me see here if I can do this more efficiently. I think this is what you're asking, Tyler. Is that correct?
Yeah.
Okay, so that's a great question. I'm glad you caught it. It's not often that this is caught. So what you're seeing here is the stress tensor. Now, of course, modified by subtracting the principal directions from the trace. And what you asked was, in row 1, column 2, I have sigma xy. In row 2, column 1, I also have sigma xy. Similarly, 3, 1 and 1, 3 are the same, and 2, 3 and 3, 2 are the same. So I kind of snuck that through. Turns out that that is true and correct. However, it requires something that you don't know yet that we're going to cover next lecture.
Okay.
Ultimately, we're going to find that, you know, I've been saying we have 9 components of the stress tensor, which we do. We have 9 components, but not all of them are unique. It turns out only 6 of them are unique, and we're symmetric across this, this diagonal. So that'll be a conclusion of next lecture.
Got it.
So Gavin asked a question. Gavin, why don't you hang out for a few minutes after everybody else departs, and you know, if it's a specific question about an email, I can answer that one privately. Any other questions from anybody? Okay, thank you all for attendance and your great questions, and I look forward to seeing you guys next week. Have a great weekend.